Greetings and welcome to the proceedings surrounding the 18th Pfizer Colloquium of the Department of Statistics at the University of Connecticut. Since 1978, the Pfizer Global Research and Development and the American Statistical Association have provided support for this program. This support has helped us to bring the most distinguished statistical scientists to our university. It has also allowed us to film the Pfizer Colloquium and a conversation for the archives of the American Statistical Association. The University of Connecticut and its Department of Statistics remain grateful to Pfizer Global Research and Development and the American Statistical Association for their continued support. Before we proceed, I take this opportunity to record some personal observations. Late Professor Harry Poston was my colleague at the University of Connecticut Stores. Harry initiated the archival videotaping of distinguished statisticians for the American Statistical Association. He was the one who developed the Pfizer Colloquium series and chaired the National Committee for Filming of Distinguished Statisticians for more than 25 years. For 25 plus odd years, Harry nurtured this program like no one else could. He was uncompromising when it came to perfection. His love and dedication for the filming of Distinguished Statisticians series were legendary. Harry Poston passed away on March 23 of 2002, but I do feel and celebrate his indelible marks in every aspect of today's proceedings. I fondly recall that Harry got me involved in these matters almost 20 years ago. With love and respect, I dedicate this session to the memory of a teacher's teacher, late Professor Harry Poston. Now I call upon my colleague, Professor Bill Williams, to take over the proceedings.
David Brillinger began his statistics career at the University of Toronto, and there he was influenced heavily by Don Fraser and Dan Delury. And after that, he went to Princeton University, and there he was influenced by many people, Sam Wilkes and particularly John Tukey. Almost simultaneously, he arrived at Bell Labs, and he was again influenced by John Tukey. John Tukey was the supervisor of that group. There were many, many people there at the time, Colin Mallows, Dick Hamming, and many others. I was in that group at the time, and I had the pleasure of getting to know David then, even though we had grown up not so far from each other in Canada. From there, David went to the London School of Economics, where he fell under the influence and began to associate with Alan Stewart and the School of English Statisticians. After that, he had another tour at Bell Labs and then went on to Berkeley. Many people know David's work for many things, and many people think of him as a mathematical statistician, and many people know him for his applied work and in all the various fields he's been working in, including environmental statistics. David has a serious lighter side, and I think later on you'll probably become familiar with that. David?
Thank you, Bill. And I want to thank Nidus for his spectacular organization of this event. And Shell Doxham, I want to thank, and he'll be participating later. Many people have had very substantial influences on my career in statistics. I will list quite a number of names at the end of this talk, just like at the Academy Awards. But the individual who has had by far the greatest influence is John Tukey. I will start with a couple of Tukey stories. I start this way because I think that knowing some human details of the great people of the field provides a better understanding of it. Once when I was teaching at London School of Economics, I visited Bell Labs, and I drove down to Murray Hill on the Garden State Parkway. At one of the toll booths, I picked up a map to learn which exit I needed to take. I noticed that on the back of the map was a send help sign. At the labs, I went to visit Bill Williams, this Bill Williams. The two of us put the map up on Bill's door, which swung out into the hallway. And in not more than 2 or 3 minutes, John Tukey appeared in Bill's office, wanting to know what the problem was. It was Superman, who had arrived to help us out. Another Tukey anecdote, more fitting to the topic of this talk, is the following. One of Tukey's favorite success stories of time series analysis concerned the free oscillations of the Earth. They arise in consequence of great earthquakes. When I told John that a seismologist collaborator, Bruce Bolt, and I had a novel way to estimate the parameters of the Earth and their standard errors based on free oscillation measurements, and that we would be in the San Francisco Chronicle the next day with the results after the next great earthquake, John's question was, what if it's in San Francisco? Touché. Now we turn to some of my own stories. A journey through random process data analysis. What do the migration paths of seals, images made by electron microscopes, firing times of neurons have in common? The answer is random process data analysis, and that is the subject of this talk. Let's start with the concept of data. A datum is a fact or a measurement or an observation. Data is the plural. A singular plural distinction is important for the purposes of this talk because in many cases of random process data analysis we have only one measurement to work with. I'm going to talk a bit now about John Tukey and Martin Wilk. These are two of the major figures of 20th century applied statistics in North America. John Tukey worked at Princeton University and Bell Telephone Laboratories. He created the field of modern data analysis. On Tukey's death a few years ago, John Wheeler, a renowned Princeton physicist, said, "I believe that the whole country, scientifically, industrially, financially, is better off because of him and bears evidence of his influence." Words of high praise indeed. Martin Wilk was Tukey's and my colleague at Bell Labs. He moved on to be Assistant Vice President at AT&T and then Chief of Statistics Canada. Both Tukey and Wilk had incredible speed of thought, they dominated conversations, and their statements were eminently quotable. Here's what they had to say about data analysis. The basic general intent of data analysis is simply stated: to seek through a body of data for interesting relationships and information, and to exhibit the results in such a way as to make them recognizable to the data analyzer and recordable for posterity. My intention in this talk is to lead you, the audience, into data analysis as an intellectual subject. I have three stories to offer. They involve elephant seal tracks, electron microscope images, and nerve cell firings, respectively. The term process has historically referred to phenomena which show a continuous change with time, to functions of time. In generalizations, time has become discrete, multidimensional, set-valued, and even function-valued. Further, continuity has taken on extended meanings as well. The data of concern have gotten steadily more complex. Basic data elements of concern now include graphs, trees, knots, tessellations, shapes, regions, cellular structures, and almost any mathematical objects. Statistical dependence is basic, and the dimensions of the quantities involved are much increased. Parameters, too, have taken on more complex forms. For example, curves or measures instead of simply numbers or vectors. An aspect worth noting is that early results that were put down at the time as excessive abstraction are now basic to practice. The studies of process data and random process models provide a major interface of statistics with mathematics, science, and technology. Now the elephant seals. This story begins with a telephone call in the spring of 2002 from Brent Stewart of Hub SeaWorld San Diego. Brent was calling with an invitation to attend a workshop on the analysis of data from time depth recorders. It was to be held in Fairbanks, Alaska. The organizer, Ward Testa, had indicated that the purpose of the meeting was to identify common problems with dive data as collected by time depth recorders and to seek solutions for dealing with the quantitative analyses of these data while addressing the various questions of interest to marine mammal biologists. I quickly agreed to participate. Helping out substantive scientists is part of the job description of a statistician, and travel is one of the perks. It turned out that a great deal of data had been gathered concerning the movements of seals, but not much had been analyzed deeply. The biologists needed help. There were 12 marine biologists and 7 statisticians, including Jeff Watson, at the workshop. The topics that the biologists had for the statisticians included describing migrations, classifying dives, identifying dive bouts, and sampling issues. After the workshop, I teamed up with Brent Stewart to work on the tracks of elephant seals. These are exquisite animals. Here is what they and Brent look like. Brent's on the left. Brent and his partner are fixing a recorder on this patient seal. Animals have to be very patient when biologists are around. Little was known about elephant seals until very recently. They were almost extinct 100 years ago. Perhaps there are only 7 or 8 left. As you see from the picture, they are massive. They dive very deeply, a mile, and they're underwater a long time, perhaps up to 2 hours, and twice a year they set off from the California coast on lengthy migrations northwest into the Pacific. A sensor is epoxied onto a seal and then recovered on the animal's return. The next figure shows a migration taking 75 days. Horizontal axis in the figure is longitude, the vertical is latitude. One sees the west coast states of the United States, but not Canada. The arrowhead indicates the outward journey. The line on the figure is kinky because the points are 24 hours apart. The points joined are the estimated midday positions of the animal. As the figure shows, the migrations can cover thousands of kilometers. Further, the animal migrates alone. The midday positions provide the datum for the analysis to be presented. The character of the route in the figure makes one think of the maps in airlines' in-flight magazines. Pilots seek to fly the shortest routes. Such paths are called great circles or geodesics, and they appear as curves on the magazine's maps. A great circle path has been included in the third figure as a reference. The outbound destination was picked by eye. Variability around the path comes from at least 2 sources: the animal's foraging and the inaccuracy of the location estimates. As this elephant seal's track does fluctuate near the Great Circle, the marine biologists have a possible mystery to consider. An initial step in analytically describing such migratory trajectories might help to develop some understanding of the mystery. This is where random processes come in. Just what is a random process? The idea is not complicated. It is as simple as picking a curve out of a hat, and this is a realization of a random process. That's some random process data. Emphasis on the random. Random processes are generalizations of ordinary chance quantities or random variables. Random processes are families of such. However, today's usage seems to have in mind that the index labeling the families has something extra, like an order or a topology or an algebraic structure. Often the index refers to time or space or both. Alternately, a random process is a probability measure on a function space. In operational use, a random process is a random function or a random measure or a random generalized function. It has domain that is temporal or spatial temporal. Its realizations are curves, surfaces, shapes, figures, sequence, and the like. It relates to situations where things move and change, things in time or space or both. Returning to the seal journeys, perhaps an animal has in mind both inbound and outbound destination. But how does it know how to navigate to these? Perhaps in the outbound journey, the animal doesn't actually have a specific destination in mind, just a general one, and can simply keep going straight ahead. For the return journey, there's a reasonable destination, the place where the animal started from, the rookery. The navigational mechanisms such an animal might employ are as yet unknown. Some speculate that a great circle route would imply that the animals are able to assess their position relative to some astronomical or global magnetic background and constantly make course corrections. As the animal seals dive and forage continuously while migrating, there is a need for such course corrections. How might data such as that in the figure be summarized? One approach is to build a stochastic model and thereby be led to pertinent quantities to compute from the data. Turning now to model development for this situation, It is to be noted that differential equations have been used to describe the motion of objects since the time of Newton. Lately, probabilists have been developing stochastic analogs, the so-called stochastic differential equations, or SDEs. The case of a particle wandering randomly on the surface of a sphere, for example, was considered by the French physicist Francis Perrin in 1928. In the case of a migration, a drift term needs to be introduced. Other aspects of the real-life problem that needed to be taken into account in the model building and analysis were that the animal's positions were available only at noon, that there were missing values, and that there was location error. With some further assumptions, a goodness of fit or likelihood function, depending upon the unknown parameters, could be set down and optimized in order to estimate the unknown quantities appearing. A diffusion with constant drift appeared to fit various of the data sets well. The error of location turned out to be more substantial than that corresponding to the foraging. It can be noted that the estimated measurement error was close to that obtained in a calibration study that had been carried out beforehand. The process here was spatial, temporal, and vector valued. The model involved a stochastic differential equation and measurement error. The data analyses included plots, smoothing, residual analysis, and simulation. Random process methodology proved exceedingly helpful in developing a description of the datum. A new random process turned up, one described by a stochastic differential equation on the surface of a sphere. The sealed datum was viewed as a segment of a realization of this process. In the course of the work, the importance of simulation showed itself. Simulation may be used for various things: for program checking, for likelihood computation, for bootstrapping, and for estimation. In the present case, the likelihood function used for estimation was estimated by simulation. Further possible paths of the fitted process were generated and compared to the ones measured in order to check the reasonableness of the model. The next figure provides an example. One sees a three-dimensional view of a particle moving irregularly but steadily across the surface of a sphere. The parameters employed in the simulation here were those obtained by fitting the stochastic differential equation, taking note of the measurement error. The path on the sphere looks not unlike those that came up in the data. The Fairbanks Workshop report has the statement: the workshop's greatest accomplishment involved connecting marine mammal researchers with statisticians expert in appropriate methods. Workshops with diverse but compatible participants appear to be one of the most effective ways to get topical research efforts organized. In the course of the work, Brent Stewart went to law school. He had become convinced that he needed to be a lawyer as well as a marine biologist in order to help the seals. This great circle approximation was a surprise and has generated various scientific conjectures as to its origin. Nowadays, there's a broad group of random processes that may be used in the development of models for process data. These include time series, markup chains, stochastic point processes, branching processes, birth and death processes, Gibbs processes, and diffusions. Stochastic geometry suggests some more: line processes, random sets, fiber processes, and tessellation. My next example comes from electron microscopy. The story begins with my biking home one day in 1987. I caught up with a neighbor, Bob Glazer, about midway home. The two of us began walking along together. We were acquainted by having sons in the local scout troop. At one point, Bob asked, "Do you know anything about the Fourier transform?" I muttered a response, and collaborative work began. Bob is a biophysicist specializing in structural crystallography. Amongst other things, he is interested in obtaining good images of crystalline substances. He obtains the pictures via electron imaging. This is a technique that biophysicists employ to learn about molecular structure, particularly the placement of atoms within molecules. The work is carried out mainly with materials that are crystalline. There one has regular replications of the basic entity, and one can enjoy the benefits of averaging. In our work, the substance studied was the protein bacterial rhodopsin. It has hexagonal symmetry as well as periodic structure. pictures were taken and the photographic films digitized on a grid by a scanning densitometer. The unit sizes are tiny, measured in angstroms, tenths of billionths of a meter. The figure shows an estimated basic entity obtained by averaging about 160 units. It is about 62 angstroms by 62 angstroms. One sees ridges and valleys, but no particularly clear structure. Having said that, it is surely an improvement over an image of a single unit. Now, I might have simulated an image of a single unit for you by adding noise to the final product, but started with the average of 160, because that is the datum that I was given. The averaging was actually carried out by Fourier transforming, taking the advantage of the periodicity of the crystal. The problems that Bob raised were to improve such images by statistical methods, to efficiently combine several images of the same material, and to assess the uncertainty of the final estimate. It was anticipated that the improvements would result from taking note of the presence of noise in an image and of the noise's particular distributional character. Fourier analysis has just been referred to. It's a very powerful tool for process data analysis. By Fourier transforming is meant using sines and cosines to isolate frequency side effects, at least approximately. John Tukey once wrote, "One can Fourier transform anything, often meaningfully." The Fourier transform was definitely important to him. I sat in a Princeton classroom in the spring of 1963 and watched John come out with a fast Fourier transform, FFT algorithm. I even reviewed the notes taken by Jim Thompson. I surely missed an opportunity there. Later, Gordon Sandy and Jim Cooley seized upon the idea and prepared Fortran subroutines for the computations. Concerning a particular Fourier inference method, Tukey has written, "My work in spectrum analysis has been an active catalyst for my ideas about data analysis in much more general contexts. A good reason for this is spectrum analysis having all the troubles of other data analysis, only more so." There are other transforms that also have fast computing algorithms and that are proving useful these days. An example is provided by the wavelet transform. Returning to the problem at hand, the structure of the crystal being periodic, it was convenient to construct a representation of it by a Fourier series or a trigonometric expansion. In the work, first an imaging experiment was carried out. This gave the scientists better estimates of the amplitudes and phases of the Fourier coefficients. Further, the scientists knew beyond the imaging that they could obtain even better estimates of the amplitudes of the coefficients by diffraction experiments. These diffraction-based amplitudes could then be inserted into the Fourier expansion, replacing the amplitudes obtained from the imaging experiment. The expectation was of obtaining a better result. There was yet another trick that the biophysicists had developed. David Blow and Francis Crick were led by a Bayesian argument to take the product of each Fourier coefficient estimate in the expansion by a so-called multiplier. The value of a multiplier was near 1 for a well-determined coefficient and near 0 for a poorly determined one. In practice since then, both averages and multipliers have been employed in constructing the final estimates. This leads to clearly improved images. The figure shows an image obtained in this fashion. It shows considerably more detail than the previous figure. Also, one sees evidence for rotational symmetry and indications of isolated peaks. There remain Bob's questions of how to combine a number of images and display the final results uncertainty. To address this, we noted that the discrete Fourier transforms of planar fields were sums. Central limit theorems suggested approximating their distributions by normals. Normal theory could then be invoked to justify weighting the coefficients from different images inversely proportional to their estimated variances. By the use of the weighted average, the problem had been reduced to the single image case. Multipliers can be introduced as before. As another extension, statistical subject matter could now be invoked to select particular multipliers other than the Blow and Crick one to employ in practice. The next figure shows in the panel on the left the result of combining 42 images. A substantial structure has appeared. One notes the threefold symmetry and the appearance of defined peaks. The procedure may be validated by comparing this result with a highly accurate image obtained by other methods. Such an image is in the right-hand panel of the figure. There is impressive agreement. The interpretation resulting from the work is there are 3 protein molecules of 7 transmembrane alpha helices, with 3 of these perpendicular and 4 tilted. There remains now the issue of how to compute and display an indication of the final image's uncertainty. The next figure provides 10 simulations of the image superposed. These simulations have been generated employing the Gaussian model that was fit to the data. The simulation procedure was convenient, for the images were contour plots. In a sense, contour lines have been generated whose width is proportional to the uncertainty of the estimate. The conclusion is that the final image is fairly well defined. Bob Glazer's statement, re the work and re the usefulness of the method was, it can be anticipated that this merging scheme will be extremely valuable for many types of biological problem specimens. The data analyses that were carried out here included plotting, Fourier inference, simulation, shrinkage, and mean squared error computations. Tools in random process data analysis include laptops, stochastic models, differential equations, and complex algorithms. Further, the techniques employed will depend intimately on the aims of the analysis. When I'm teaching and lecturing, I like to intersperse the material with jokes and stories. The topic is meant to refer somewhat to what's going on at the time in the class. Here's something that has just occurred to me. I was intending to become an actuary during most of my studies, but I got led into statistics by Don Fraser at the University of Toronto. I had a good friend at high school and university, John Gardner, who did become an actuary and even president of the Sun Life Assurance Company of Canada. Once his elder daughter asked me a question that she herself had been asked. What's more boring than becoming an actuary? Her answer, nothing. Now, that is simply untrue. Actuaries have developed many tools that statisticians have found exceedingly useful, including life tables, smoothers, and the force of mortality or failure rate. The actuaries have worked out probabilities for some very complex events, starting the computations 300 years ago. Now I move on to a question that one of my students, Knut Asa, asked me. What's the difference between an actuary and a member of the mafia? His answer, the mafioso can tell you both when you're going to die and where you're going to die. Let's move on now to our final example. It concerns the sequence of times at which nerve cells fire, the so-called spike trains. The example addresses the problem of the identification of a nerve cell system. Pepe Segundo, a professor at the Brain Research Institute at UCLA, came up to Berkeley to give a seminar on point processes. The seminar was being run by Peter Lewis and David Beer-Jones in the early 70s. In the course of his presentation, Pepe indicated that he had many data sets of neurons firing times. I asked if I could work with some of that data to try out some methods that I'd been developing for point process system identification. A steady stream of boxes of punch cards began to arrive at Berkeley from Los Angeles. What is a point process? A point process refers to elements scattered about in some space. In our case, the space is the timeline. The top graph in the figure provides an example, representing the points by short vertical lines. What is a system? A system is the collection of an input, a function that operates on the input, and the output. What is system identification? The procedure of learning the characteristics of a system on the basis of input and contemporaneous output. Let's return to nerve cells specifically. In Pepe's experiment, a neuron, L5 of Aplysia californica, or the C hair, was stimulated to fire repeatedly by an inserted fluctuating electrical current. The bottom graph of the figure provides the stretch of input corresponding to the neuron's firing times in the top graph. It's difficult perhaps absolutely impossible to see any connection between the input and the output here. The methods that I've been working on sought to assess specific quantitative measures of serial dependence involving point processes. They were point process analogs of the correlation and regression methods of ordinary statistics. That early work eventually led to a success story. Namely, we were able to infer the wiring diagram of networks of 3 neurons by a partial coherence analysis. The computations involved Fourier transforms. The particular work to be discussed just now, though, is the building of a conceptual model of a neuron's firing. The model seeks a probability intensity function for the firing of the neuron, as it depends upon the input employed and the stochastic entities involved. This intensity function is a generalization of the actuary's force of mortality. An ubiquitous concept in the work of statisticians, and indeed of all researchers, is that of a model. A variety of meanings are attached to the word. Here it is taken to be a mathematical simplification of a reality. With a model at hand, much of a researcher's work becomes deductive and manipulative. The greatest difficulties lie in creating pertinent models. Statisticians end up with schizophrenic attitudes to them. In a 1962 paper, Martin Wilk is quoted as saying, "The hallmark of good science is that it uses models and theory but never believes them." So be it. Consider the following model. An electrical input contributes by a filtering or summation to the membrane potential within a neuron. The neuron fires when the potential crosses a threshold at a so-called trigger zone. There are some other neural phenomena that need to be included in the model. For example, the refractory period. This refers to the phenomena that once a neuron has fired, it refrains from firing again immediately. In the model we built, this is handled by, after firing, resetting the threshold to a higher level for a time period. The character of the filtering the input undergoes affects whether the neuron is excited or inhibited by the stimulation. Assuming the threshold level to be Gaussian or normal, a likelihood function can be set down and employed to estimate the summation function and other quantities. The results are presented in the remaining figures. The first figure presents an estimated linear kernel, and the second an estimated quadratic kernel. The linear is a function of one time lag running along the x-axis, the quadratic of 2 time lags along each of the axes in the figure. The linear kernel in the figure shows a strong positive swing around a time lag of 1/10 of a second, followed by a rebound to lesser negative values. On the other hand, the quadratic kernel shows a negative swing around the time lags of 1/10 of a second. And in this plot, which is a contour plot, as you see, the negative contours are denoted by solid black lines. Perhaps this negativity that has turned up is meant to compensate for the linear kernel being too large, around 1/10 of a second. Now, what is a kernel? The linear and quadratic kernels here may be compared to the coefficients b and c in the quadratic expression a plus bx plus cx squared. The distinction is that in this high school case, x is a number. Here it is a function, and time lags are included. Returning to the neural system, in the model, the kernel terms add together to give the membrane potential. The bottom panel of the last figure provides an estimate of the membrane potential itself, while the top panel graphs the actual firing times. One can note some large values of the estimated membrane potential near the firing times. It's worth emphasizing here that the parameters have conceptual interpretations. Also, that the model allows spontaneous firing of the neuron. And finally, that the model can handle the aging of a neuron by including a trend or a non-stationary term. Data analyses employed in this example included plotting, probit analysis, function estimation, and smoothing. Validation was carried out in part by estimating the assumed normal distribution non-parametrically, using the just mentioned comparison of firing times with the estimated membrane potential. Concerning such statistical work, my friend and collaborator Pepe Segundo has remarked that The ultimate goal is understanding in strictly biological terms. Statisticians need to remember that. We end with some summary conclusions and then acknowledgments. The talk has focused on process data analysis and presented 3 applications: seals, molecules, and nerves. The data types were a curve on a sphere, images, time series, and scatter. There have been surprises, assistance provided, and understanding gained. The 3 examples presented have much in common: the need for sophisticated data collection and analysis hardware, the need for flexible software, the need for subject matter specialists, the need for high-quality data, as well as random processes, and of course, data analysis. Analytic problems have abounded, as have substantive questions requiring analytic formulation. Similar methods are seen to play central roles in these quite highly disparate fields. In a paper that I wrote about 30 years ago, stimulated by working with Pepe and his data, I sought to describe some of the stages involved in a modern applied statistics problem. These included: first, the experimenter collects interesting data. Second, the experimenter recognizes relevant scientific parameters to estimate. Third, the experimenter consults a statistician as to whether or not his estimates are significant. Next, the statistician suggests means of assessing sampling fluctuations and possibly suggests transformations in order that the data may be more simply described. And finally, the experimenter and statistician collaborate to determine and fit a statistical model and to design further experiments to confirm the model. The paper's remarks continued with: the experimenter must learn a fair amount of statistical methodology, and the statistician must learn a fair amount of the experimenter's subject matter before any real progress can be made. That was my experience in 1975 and remains up to today. We end with some wise words of others. First, Sherlock Holmes in The Adventure of the Copper Beeches. "Data, data, data," he cried impatiently. "I can't make bricks without clay." Indeed. Another individual who had a very substantial influence on my work was Jerzy Neyman. He wrote in 1960 this many times since validated remark: "Currently, in the period of dynamic indeterminism in science, there is hardly a serious pace of research which, if treated realistically, does not involve operations on stochastic processes. The time has arrived for the theory of stochastic processes to become an item of usual equipment for every applied statistician." Once again, indeed. Now, it would be totally remiss, if not unprofessional of me, not to mention some of the many persons who have influenced random process data analysis besides Tukey and Neyman. These include Harold Kremer, Ulf Granander, David Cox, Morris Bartlett, Murray Rosenblatt, Manny Parson, David Donahoe, Andrei Kolmogorov, Ted Hannon, Norbert Wiener, Peter Lewis, David Kendall, David Beer-Jones, Hirotugo Akaiki, George Box, Gwillem Jenkins, Morris Priestley, and the list goes on. I thank the American Statistical Association's Committee on Filming Distinguished Statisticians. Little did I ever expect to be one of those filmed. I thank Pfizer Incorporated for sponsoring these filmings. I have to say that it's pretty nice to be made a fuss about. I have a bunch of other people to thank, and I list some. My high school math teacher, Nails McLean. He was called Nails because he was also the hockey coach. Don Fraser, Jim Durbin, David Blackwell. Got good stories about all these people, but not enough time to tell them. Lucien Lacombe, Elizabeth Scott, Pepe Segundo, Brent Stewart, the guys at Bell Labs, Roger Pinkham, Colin Mallows, Bill Williams, Martin Wilk, Ram Nanadesikan, Fred Mosteller, Bruce Bolt, Hilgard O'Reilly Sternberg, Bob Glazer, my wonderful students, and my dear wife, Lori. I was lucky. I had many mentors and role models and good students. Thank you.
Thank you, David, for a wonderfully stimulating lecture, and thank you, Bill, and thanks to you all.